I'm here to present work done by quite a large group actually at our faculty, a group working in the intersection of algorithm and structural graph theory. The main work within this area is supported by two ERC grants. One is led by my brother Michał Pilipczuk. This is grant Kutacoms, which is close to being finished. It has one more year, and there is a new grant, Bob, led by me that just started last month. So essentially, this is a large group supported by two ERC grants at the moment. So apart from the two of us, there are multiple other people working within these topics. For instance, out of people who might be here, Łukasz Kowalik, Paweł Rzążewski, Szymon Toruńczyk, Anka Zech-Pawlewicz, but also a host of PhD students and several other people around, and we have a lot of connections in the world. Good. So essentially what we are doing here, we are working on graph problems predominantly, and we are working on hard graph problems, mainly NP hard graph problems. So if you think about an NP hard problem, you expect that you cannot solve it in polynomial time, so you can approach it in several different ways. You can make some heuristics, you can do approximation algorithms, this is also what we do. You can think about making an exact algorithm that will work in exponential time, but maybe you try to make this exponential as best as possible. What we are focusing on mostly is parameterized algorithms. Not only, but this is somehow a key theme here. So the idea behind this parameterized algorithm, if you haven't seen this field before, is that essentially instances of hard problems are not equally hard in a sense. For instance, if I think about the k-path problem, looking for a simple path, a path without self-crossings of length k in a graph, then looking for a k-path of length 5 should be simpler than looking for a k-path of length 100, right? So this 5 or this 100 is now our parameter that sort of measures the hardness of the instance. So the brute force algorithm for this problem would run, say, in n power k time, just enumerate all the possible k tuples, but you can do much better. You can actually, there's several different, very different techniques in parameterized complexity, like algebraic techniques, color coding, representative sets, or some decomposition-based methods like tree with tree depth, that can give you a fixed parameter tractable algorithm for this problem. And this is an algorithm with running time exactly like the one here. Yeah, so some function of k, some function of the parameter, sometimes some fixed polynomial, say c equal to, I don't know, 10. And this kind of algorithm, FPT algorithm, there is a non-trivial theory how to get them. It is rich in very many different tools. We actually wrote a book some years ago about this topic. You can see it online. So the field of parameterized algorithms is mostly about techniques for designing efficient FPT algorithms. And the nice thing about this field that I really personally like is that this is not a field about, I don't know, shaving log factors or doing some algorithm engineering. This is really a field about understanding the combinatorics of the problem and understanding it to the point where you can actually take the problem and place into some specific complexity class. And these tools that you use here are very often connected to classic work in graph theory, and in particular in structural graph theory. So a part of graph theory that is about describing structure in graphs, decomposition, for instance. So because we are working with structural graph theory, it is often the case that we do not work on general graphs, but we work, for example, on some specific graph classes. So we design algorithms working, say, on planar graphs, or graphs with maximum bounded maximum degree, or graphs of bounded tree width. If you know what is tree width is the composition measure that tells that the graph roughly looks like a tree. And so on and so on. Yeah, so there is a lot of interplay between graph theory and algorithms. And this is more or less the main theme of what we are doing. We are looking at classic results from graph theory, and we are using graph theoretical tools to design efficient algorithms, and also the need of designing algorithms give us some insight into what nice results in graph theory one could think of. So the interplay between those two fields, this is the main area of our work. So given this picture, I usually like to add one more corner to this picture, and this is also what some subset of us is working on, namely logic here. Yeah, and these three aspects, the logical aspects, combinatorial aspects, and algorithmic aspects, they really create this triangle or this area in which we are working. So to make it more precise, what do I mean by logic on graphs? So you can, if you think what should be a logic on graphs, there are several natural models you can think of. For example, first order logic would be probably the most natural one. You can, for example, say that there is a triangle in a graph, so you can quantify over single vertices and check adjacencies. There are some more complicated logics, more expressive logic, like monadic second order logic, where you can quantify over subsets of vertices, for instance. So you could phrase in this way, say, free correlability of a graph. So you already see that with a formula that is really simple, you can express an NP-hard problem. Yes, so given these models of logic, you can speak about the model checking problem for a logic. So you are given a graph, you are given a formula, so a description of a problem, if you say, and you would like to check whether this formula holds in the graph. So check whether the graph has some properties expressible in your logic. And this is a problem that is naturally parameterized by the size of the formula. So the main goal in this logical part, this meta algorithmic part of our work, is to understand this correspondence. What kind of logic, like logical formalism for expressing problems, correspond to what classes of graphs in terms of that this logic behaves well on this class of graphs. And this behaves well is expressed in algorithmic terms, that we are looking for FPT algorithm for model checking. Yeah. So in order to understand this correspondence, you need to understand all three corners of this triangle. Yes, because you need to understand the graph theoretical properties of your class of graphs that you are working on. You need to understand the logic that you are working with, and you need, at the end of the day, to design an algorithm. Good. So there are multiple problems that you can think about in this area, and many of us say lie in different parts of this triangle. I probably would place myself somewhere here, more closer and closer with years to the logical part. Marcin is probably somewhere here. Szymon Torunczyk is even more to the logic, probably somewhere here. Paweł Rzążewski, perhaps maybe here. Łukasz, I don't know where you would place yourself, maybe somewhere here. I don't know, but essentially there is a lot of interplay. Different people here like different things, but we all work together on different stuff, and this interdisciplinary nature of this area really gives really interesting, mathematically interesting results. So to give you some flavor of concrete problems that we are working on, these are actual problems, big open problems that we were considering in the past years. So for instance, let me talk about the independence set problem in PT3 graphs. So the independence set problem, I guess you have a graph and you want to find as many vertices pairwise and adjacent as possible in your graph, and we are working on PT3 graphs, so graphs that do not contain a path on T vertices as an induced subgraph. So for example, this is a P4, and the P4 graph doesn't contain the 4 vertices that create exactly this pattern of adjacencies. And then you can ask independence set in PT3 graphs, is it, say, NP-hard, polynomial time solvable? And this turns out to be a very interesting problem. So there is a polynomial time algorithm, a very simple one in P4 free graphs. It was a very long, for a long time, open problem whether on P5 free graphs it is polynomial time solvable, and this was solved in 2014. In 2017, we solved it on P6 free graphs, and the P7 free case is currently actually open, whether it's polynomial time or not. However, last year there was a breakthrough result of Gartland and Lokshtonov, who gave an algorithm that works in quasi-polynomial time for every fixed t. So for example, on P100 free graphs, you've got n power log cube n. So we managed to get the running time slightly better and power log square n recently. And really, this algorithm is 3 lines. Maybe not 3 lines, but half a page algorithm. So this is really a simple result that is completely new. And now the question is, can you, using these techniques, actually get a polynomial time algorithm for any fixed t? Okay, so maybe I will skip this one. I will just mention at the very end a logical problem about FO model checking. So I told you about these 2 different types of logic, monadic second order logic and first order logic. And we would like to understand the correspondence between like algorithmic tractability of this logic and various classes of graphs. For MSO, this is well understood, and these are classes of, let's say, tree-like graphs. But for first order logic, we don't really understand what is here. Probably we don't understand. We understand what is here in sparse graphs. This is the notion of nowhere denseness. However, we are having now, I think, a good guess on what should be this question mark in here. And this is the notion of being monadically NIP. And this is a notion that is borrowed from model theory. So we are trying to construct a structural graph theory for monadically NIP classes and so-called monadically stable classes in order to understand them well enough so that we can design efficient algorithm on such graphs. And this would encompass all the well-behaved classes of graphs like excluded minor, planar graphs, bounded degree graphs, and so on and so on. So this is really a fundamental direction here. Good. So thanks a lot for listening, and yeah, I hope to chat with you about more details in the break later on.